Simple harmonic motion. Nature provides many examples of vibrating systems, for example, trees swaying in the wind, motion of the tides, etc. For all these systems, some things are similar. For example, the motion has to repeat itself in equal intervals of time, and some force constantly acts to restore the system towards the point of equilibrium. This motion is also called a periodic motion. The period of the harmonic motion is defined to be the time required for the vibrating body to complete one round trip, which is also called a complete oscillation or one cycle. If the particle in this periodic motion moves back and forth over the same path of the motion is said to be oscillatory or vibratory motion. A simple example of oscillatory motion is Mang hanging from a spring, and you let go of the mass and it oscillates and it comes back to its original position. The position at which no net force acts on an oscillating particle, or in other words, where an object is at rest, is called its equilibrium position. The displacement is then defined as a distance of the oscillating particle away from its equilibrium position at any instance of time. Larger displacement will mean that the vibration of the particle is large. So what is restoring force? A force will be called a restoring force when it acts on a particle in such a way as to accelerate the particle in the direction of its equilibrium position. If the system is disturbed from its equilibrium, the restoring force will try to bring it back towards its equilibrium. For example, if you have a pendulum, which is just a mass attached to a string, and you let it go, it will start to oscillate, right? So restoring force will bring it back towards its equilibrium so that it basically just hangs there. However, inertia, when it gets to that point, inertia will cause it to go forward, and then a motion like this will be set up. Or in this animation, you can see it going back and forth, up and down, and in this form, forming a simple harmonic motion. Another way to think about what restoring force is the force by which a body resists deformation. The applied and the restoring force are equal in magnitudes but opposite in direction, according to Newton's third law, forming the action and reaction pair. Under static condition, the restoring force with which an elastic body opposes whatever pull or push is applied to it often obeys Hooke's law. And the Hooke's law is stated as the magnitude of the restoring force is directly proportional to the deformation. For a mass attached to a spring, Hooke's law is a good approximation that provides the deformation, provided that the deformation is small. So F, which is the restoring force, is equals to minus kx, where k is the spring constant and x is the displacement away from equilibrium. SHM, simple harmonic motion, is a very special kind of oscillatory motion in which the restoring force is proportional to the displacement from the equilibrium point, and an object that experiences simple harmonic motion is called a simple harmonic oscillator. There are many examples of simple harmonic motion in real life. Any spring or rubber band with a weight attached that is free to vibrate will exhibit simple harmonic motion. Similarly, a pendulum, including a child on a swing set, exhibits simple harmonic motion. For a system in simple harmonic motion, period is independent of the amplitude or the size of the vibration. The frequency of the vibration is the number of oscillations per second, so frequency is directly proportional to t, where t is the period. So frequency is also cycles per second, how many times something oscillates per second, and the unit is called hertz. Some properties of simple harmonic oscillators. All simple harmonic oscillators have to have these properties. 1. The force that an object in simple harmonic motion is called a restoring force, and the restoring force will be given by Hooke's law. The magnitude of the restoring force has to be proportional to the displacement from the equilibrium point, and the frequency and hence the period of a simple harmonic oscillator is independent of its amplitude. Some examples of simple harmonic oscillators include the simple pendulum. Simple pendulum is simply a mass attached to a thin rod or a lightweight string, where the mass is much smaller than the length of the string, and the amplitude of the oscillations is considered considerably small. So the theta in this case will be considered considerably small. The period of this oscillator will be given by 2 pi square root L over G, where the equilibrium point is directly below the suspension point at which the pendulum will hang motionless. Number 2, a physical pendulum. A physical pendulum could be any rigid object that is free to oscillate about some fixed axis. The period of an oscillation of a physical pendulum is not necessarily the same as that of a simple pendulum. Torsional pendulum is a special kind of pendulum which is made by suspending a mass, say a bar or a disc, attached to a string and by twisting it by an angle theta. It is quite similar to a simple pendulum except that the twisting motion as the string unwinds provides the oscillation in this pendulum. The restoring force is essential for simple harmonic motion that's provided by the gravity, and as the string shortens it twists and lengthens as it untwists. Another really good example is a mass attached to a spring. So if you have a mass which is attached to a spring and it is free to oscillate, it will actually form a simple harmonic motion. So as you can see with the black line here drawn, it shows us where the different points is going to be. So any motion that repeats itself and it is nice and smooth like a sine graph is called a simple harmonic motion. Another way you can form simple harmonic motion is instead of the pendulum swaying this way, you could also, if you hold a string and you twirl it around and around, that will actually be also simple harmonic motion. So if you were to take an example. If you have a light on the top, take your hand and move it in a circular motion. And what you will observe is that the shadow of your hand is actually undergoing a simple harmonic motion. So as the circle rotates, its projections move to and fro along a straight line, and this to and fro motion can be plotted onto a graph, and when traced on the graph, it will be a sinusoidal wave pattern, implying that this is simple harmonic motion. Energy breakdown of an object undergoing simple harmonic motion. So conservation of energy states that the total mechanical energy of the system undergoing simple harmonic motion is constant. So when you have a displacement, let's suppose that this is your equilibrium point and your pendulum is free to oscillate between maximum A and minimum minus A. So as you move, if your oscillation is at maximum direction away from it, its speed at this point will be 0, its amplitude will be maximum, kinetic energy will be 0, and the potential energy will be maximum. At equilibrium point, on the other hand, maximum the other way around, same thing will happen, speed will be 0, kinetic energy will be 0, potential energy will be maximum. At point of equilibrium, however, you will have maximum kinetic energy, minimum potential energy, actually 0 potential energy. For a vibrating mass spring system, the frequency of vibration is given by this formula. Frequency is equals to 1 over 2 pi square root k over m, where the frequency units are going to be hertz. Now we know frequency for a simple harmonic oscillator is 1 over t, right, where t is the period. So this implies the period of a vibrating mass spring system is given by 2 pi square root m over k. Now let's consider an example. Suppose a certain mass stretches 0.01 meters when loaded with a 2 kilogram mass. Find the spring constant. At what frequency will it vibrate when it's loaded with a 2 kilogram and a 0.0 kilogram mass? So what does the question say? So it says that I have a mass attached to a spring, and it says that it stretches, so its y or x is 0.1 meters under the influence of a mass which is 2 kilograms. I have to find the frequency when it is loaded with a 2 kilogram mass. 2 kilogram mass. So how do I write this? Okay, what I'll do is I will write it frequency when it is loaded with a 2 kilogram mass and frequency when it is loaded with a half kilogram mass. Now what is the formula for frequency of a mass attached to a spring? So I know that my frequency is going to be 1 over 2 pi square root k over m. Good. I have the masses that I'm going to need, so they give me 2 kilograms and 0.5. The problem is I don't know what the spring constant for this spring is, but can I calculate it given this information? And the answer is absolutely. What do I know? I know that if I have this mass and it's hanging, it is going to have a weight which is going to be acting downward, and it is going to have a spring force which is taking it upward, which is going to be kx. So now how do I fix it? I know that the net sum of my forces has to equal 0 because the system is at rest. This means that the kx, which is a spring force, minus mg, which is acting downwards, has to equal 0. Or kx equals mg, right? Or k will be equals to mg over x, where x is the stretching force, right? In this case, what did I call my stretching force? Y. So I can replace this x with a y, okay? So now I have everything I need in order to calculate k. What do I have? I have my mass, which is 2 kilograms. I have my g, which is 9.8 meters per second squared. And I have my y, which I know that the stretch is 0.1 meters. So plugging all of these numbers in and putting them into your calculator, I calculate my k to be 196 newtons per meter. Now I have everything I'm going to need in order to calculate my frequencies. So I have my k and I have my m. Note, k will not change when you change the masses, right? So for the first case, for this frequency, what will I get? 1 over 2 pi square root k over m. Plugging the value of m, I will have 1 over 2 pi square root k, which is 196, divided by mass, which is 2 kilograms, right? And I plug these numbers in, and I calculate my frequency to be about 1.57 hertz. Okay? For number 2, following the same exact formula, 1 over 2 pi square root k over m, which is 1 over 2 pi square root 196 divided by 0.5. Again, note the value of the spring constant does not change by changing the mass attached to the spring. And I'm going to leave that as an exercise for you.